Hello, my name is Arne Telle, and I will be presenting the paper Perfect Matching Cut Revisited. This is joint work with von Bangle from the University of Rostock in Germany. So what is a perfect matching cut in a graph? Well, it's a subset of vertices S, such that if you consider all the edges going between S and the complement of S, then those edges give exactly a perfect matching of the graph. No other edges go between S and the complement of S. So in particular, this tells us that the number of vertices in S must be half of the number of vertices of the graph. Okay. So for example, a hypercube has a perfect matching cut. A hypercube of any dimension has a perfect matching cut. You see it from the recursive definition, where you make a hypercube of dimension k by taking two smaller hypercubes of dimension k minus 1 and actually adding a perfect matching. Okay, so this hypercube here of dimension 3, it has these three perfect matchings depending on how you make the cut. Okay, so the question we will be addressing is the question of, given the graph G, does it have a perfect matching cut? So this problem has not been studied much before. It was shown to be NP-complete back in 1998. Since it can be expressed as a monadic second-order logic problem, it is FPT parameterized by tree width and by the clique width of the graph. Moreover, since it is two-partitioning sigma rho type problem, where you set the values of sigma and rho to be 1, this problem is xp parameterized by the mim width of a graph. Mim width is what's known as the maximum induced matching width of a graph. This means that this problem is polynomial time solvable on classes where a bounded mim-width decomposition can be computed in polynomial time. So this follows from results of 2012 and 2013. Yeah. So in particular, for interval graphs and permutation graphs, this will give us an algorithm with runtime order n to the 10. But n to the 10 is a very slow polynomial time runtime, and it seems that we could do better. So this is partially the reason why we revisit this perfect matching cut problem in this paper. Okay, so what are the results that we have? Well, we have some negative results, some hardness results, and we have some positive results. Let me start by mentioning the negative results. So we show that it is NP-complete already on a quite restricted class of graphs. It is NP-complete even if the input graph is a bipartite graph of maximum degree 3 and arbitrarily large girth. Notice that this means that if I look at the class of age-free graphs, where I do not allow an induced subgraph isomorphic to some small graph h, then if the small graph h has a vertex of degree larger than 3, or if it has any cycle of a fixed size, then it will remain NP-complete on that class of graphs. Okay, we show also that on n-vertex bipartite graphs, unless the exponential time hypothesis fails, we cannot have an algorithm which is sub-exponential in the number of vertices. And for bipartite graphs having maximum degree 3 and arbitrary girth, we cannot have an algorithm to the little o of a square root of the number of vertices. Okay. On the positive side, we give an exact algorithm with runtime 1.2721 to the n, and we also give two classes of graphs of unbounded mim width where the problem can be solved in polynomial time. The first is the class of t-free graphs, where t is the tree below here on 6 vertices, and we notice that this tree has indeed maximum degree 3 and no cycle, right? We can also solve it in polynomial time for a class of graphs which contains the chordal graphs. We call these the pseudochordal graphs, and they can be defined as being those graphs where every edge of any non-trivial block belongs to a triangle. We'll get back to this. I will not be giving the proofs here in any detail at all. I then recommend that you look at the paper if you are interested in the detailed proofs, but I will sketch how we arrive at these results. I will start then with the reduction showing the NP completeness. Okay. So this reduction is from the problem known as positive not all equal 3-sat. Okay, this is an instance of satisfiability in conjunctive normal form where all the literals are positive. Okay, and what we are asking for is an assignment where every 3 clause has at least one true and at least one false variable. Okay, so if we're given such a formula, we will construct a graph, and we will be doing it by a clause gadget and a variable gadget. Okay, so the clause gadget will be actually a hypercube on 8 vertices, and so for each clause we have such a hypercube on 3 vertices, and it'll have the 3 vertices cj1, cj2 and cj3. Okay, and the first thing to notice is that any perfect matching cut will not put all these 3 vertices on the same side of the cut. Okay, so this will actually allow us to conclude that any assignment that has at least one true and one false will be able to be transformed into a perfect matching cut, and vice versa. If you have a perfect matching cut, then we'll be able to transform it into an assignment where there is at least one true and at least one false, not all 3 and not all false. So for the variable gadget, it is very simple. We have a vertex x1 for the variable x1, and it is connected to a sort of dummy vertex x1 prime. This will be the only edge to this x1 prime, and that edge will actually be an edge of any perfect matching cut of this graph. And the vertex x1 is then moreover connected to the 3 the clauses that it belongs to. So this x1 belongs to this particular clause and to this particular clause. Okay, and it's connected to one of the 3 clause vertices in this clause gadget, and similarly one of the 3 clause vertices in this clause gadget. Okay, and the important thing to notice then is that in any perfect matching cut of the resulting graph, these edges incident to the variable vertices that connect between a variable vertex and a clause gadget will not be part of the cut. Okay, so these aspects I have mentioned here allow us to conclude that the formula has a not all equal assignment if and only if the resulting graph has a perfect matching cut. Okay, and since it is known that this problem, positive not all equal 3-sat, unless the exponential time hypothesis fails, it does not have an algorithm sub-exponential in the number of variables. This shows that our problem on bipartite graphs, because you can also check that this resulting graph is bipartite, does not have an algorithm sub-exponential in the number of vertices. Okay, but we had the result for the special case of bipartite graphs with no vertex of degree larger than 3 and large girth, and for this result what we do is we use the reduction from the same problem, but we now subdivide the edges in the clause gadgets to extend the lengths of the cycles, and we also extend the vertex gadgets to now be cycles, and we connect these things together in such a way that the variable vertices will not have degree more than 3. The resulting graph will also have a number of vertices which is quadratic in the number of variables, and this allows us to show this result, namely that for such bipartite graphs with maximum degree 3 and arbitrary girth, the perfect matching cut problem cannot have an algorithm of runtime 2 to the little o of the square root of the number of vertices, unless the ETH fails. Okay. So those were the negative results. For the positive results, the bulk of our paper is taken up by this exact algorithm. It is based on previous work that has been done on what's known as the matching cut problem. So in the matching cut problem, you again ask for a set of vertices S, but now what you require is that the graph induced by edges going between S and the complement of S is a matching. Okay, you no longer require that it touches all the vertices of the graph, but simply that it is a matching, that there are no other edges crossing than except these matching edges. And this problem has seen a lot of attention lately, and in particular these 3 papers here by Chen, Xi, Le, Bang Le and Peng from this year, a paper from 5 years ago by Dieter Kratsch and Bang Le, and a paper from 2 years ago by Le and Bang Le. They all give branching algorithms for matching cut of various types, and we adapt these rules that are used for matching to our perfect matching cuts, and we also add a few new reduction rules and branching rules. So in total we end up with 8 reduction rules and 7 branching rules, which allow us to show this result, that perfect matching cut problem can be solved in this runtime, 1.2721 to the power n. And I should mention that this is a better runtime than what is known for the matching cut problem. For the matching cut problem, the best known algorithm has runtime 1.328 to the power n. Okay, so we mentioned also that we have polynomial time algorithms for 2 graph classes of unbounded min width. So the first one is when we exclude a small tree T, which is the tree T that we see here, where you can view it that it's a claw where 2 of the edges of the claw have been subdivided. Okay, so the graphs excluding these are claw-free graphs, which have unbounded min width. So given such a graph G, which does not contain this tree T as an induced subgraph, the way our algorithm works is by fixing an edge AB of the graph G, and then we decide if G has a perfect matching cut that separates these 2 vertices A and B to 2 different sides. Okay, and it's not difficult to see that if I know that A has to be on one side and B has to be on the other side, then some other vertices have to be on the side of A and some other vertices have to be on the side of B. And what we do is we add a 9th reduction rule to the 8 that we had on the previous result that actually do this movement of vertices over to the A side and movement of vertices over to the B side. And when we are done, then none of these reduction rules can be applied anymore. Then we call by F the set of vertices that have not been decided, whether they should belong to the A side or the B side. Okay. Well, then if the vertex set F is empty, well, then this PMC, perfect matching cut problem, is easy to decide. You're basically given this only possible cut that you have, and it's just a question of checking it. And otherwise, if there are still some vertices left in F, then the answer is no, because then either the graph G cannot have a perfect matching cut separating A and B, or it would actually contain the tree T as an induced subgraph. So we run this algorithm then for every possible edge of the graph G, and in each time we spend polynomial time. So in total we get the theorem here that the perfect matching cut problem is solved in polynomial time if the graph G is T-free. Okay, so what about interval graphs? So I mentioned that the interval graphs had bounded min width, and that we hence get an n to the 10 algorithm for deciding if it has a perfect matching cut. But indeed, it can be done much easier by some very simple observations. If we my cat is calling me here. If we have a set of vertices U that induce a connected graph, and every edge of this vertex set belongs to a triangle, every edge of this induced graph belongs to a triangle, then it is easy to see that in any perfect matching cut of the graph, all these vertices have to be on the same side. Right? If you take a triangle, you cannot have two vertices of the triangle belonging to one side of the cut and one vertex to the other side, because then this vertex on the other side would have two neighbors across the cut, and it should only have one neighbor across the cut. Okay. So if an interval graph G has a cycle, well, then it has a triangle, and all those vertices then have to be on the same side of the cut. But then each of them will need to have a private neighbor on the other side of the cut. And that means that we would have an asteroidal triple, and this would contradict the fact that the graph is interval. So if an interval graph G has a perfect matching cut, it has to be a tree. And the only interval graphs that are trees are the caterpillars. And moreover, it is not hard to see in a caterpillar, if you have a vertex with two leaves, then again it cannot have a perfect matching cut. You can have at most one leaf for a caterpillar, and in a caterpillar that has a perfect matching cut. So this is then the statement that an interval graph has a perfect matching cut if and only if it is a caterpillar with a basic path x1 to xk, drawn as a straight path down here, such that for any leaf between the two endpoints of that path, they must have either 0 or 1 leaf. That's the only possibility. And in addition, the requirement is that if you have a subpath with 0 leaves, then that subpath has to have an even number of vertices in it. Okay, so here's a positive instance where here you have a subpath of 2 vertices without any leaves. Here you have a subpath of 2 vertices without any leaves, and here a subpath of 4 vertices without any leaves. And indeed, the red vertices would induce a perfect matching cut. And this is this statement is easy to convert into a polynomial time algorithm to decide it much easier than the n to the 10 algorithm that follows from the bounded min width. Okay, so that's interval graphs, but what about chordal graphs? Chordal graphs are known to have unbounded min width, and indeed we can solve this problem in polynomial time also for chordal graphs, but we can do it for a slightly larger class of graphs than the chordal graphs. This is what we call the pseudochordal graphs. So first off, the blocks of a graph are the maximal 2 connected subgraphs, and we call the graph pseudochordal if for every block of at least 3 vertices, every edge of that block belongs to some triangle. Okay, so this is certainly the case for chordal graphs, but you see it will also hold if you take, for example, a large cycle, and to every pair of adjacent vertices you add a single common neighbor, then this would also be a pseudochordal graph. So how do we solve the PMC problem on the pseudochordal graphs? Well, we first compute the blocks of the graph G, and then we let D be the subgraph of G formed by the edges of the non-trivial blocks of G, so i.e. the blocks of size at least 3. And by collapsing each component of this subgraph D into a supernode, we see that G has a tree structure. So here is an example of such a graph. You see, actually it's not the chordal graph, because here we have a cycle on 4 vertices, right? So this is not the chordal graph. But what we have done is we have taken every maximal 2-connected subgraph that contains at least 3 vertices and forms a connected subgraph, and made it into what we here call a supernode. So we have these supernodes D1, D2, D3 and D4, and then we see that collapsing those into a single node, we get this tree structure. And by fairly standard dynamic programming algorithm going bottom up on this tree structure, we are able to solve the perfect matching cut problem in polynomial time on these graphs. Okay, that is actually an overview of our results. Now let us see the open problems that we leave. So we decided that this was polynomial time solvable for particular small tree T on 6 vertices, and we know that if the tree has a vertex of degree more than 3, then it will be NP complete. But if we take just a general F fixed forest with maximum degree at most 3, for any such forest, it would be interesting to see what is the complexity of a perfect matching cut restricted to such a F-free graph. Generalizing the other positive result, we could ask for k-chordal graphs. So the chordal graphs are 3-chordal, so they don't have any induced cycle of length greater than 3. The k-chordal graphs weaken this condition and simply say we don't have any induced cycle of length greater than k. We were not able to show a result for k-chordal graphs in general. Okay, and then another thing that has been studied heavily for this matching cut problem is recently the counting and enumeration versions of it, and also one could ask about FPT and kernelization algorithms for perfect matching cut. Okay, and with that my presentation ends. Thank you very much for the attention.